And next up, we have Martin Kuemmel from Ludwig Maximilians University in Munich, Faculty of Physics. And Martin today will talk to us about tiling the Euclid sky. Thank you, Martin.
Hello, good day, and thank you for giving me the opportunity to talk about tiling the Euclid sky, work I'm doing together with Thomas Vassallo from LMU Munich and Christophe Dabin and Javier Gracia Carpio from MPE or CNES, respectively. Euclid has been mentioned a couple of times. Here is my summary of the mission. A small telescope, it doesn't need to be very big because it's in space out there. We do have two instruments, this instrument, basically summing up GRIZ data, and an infrared instrument which gives photometry, but also slit spectroscopy with a limited resolution. Field of view, you can see here it's very large, at least for a space instrument. We are going to do surveys. We do a wide survey of 15,000 square degrees and a deep survey with 40 square degrees, mainly for calibration, but of course it has also its own science merit. As has been mentioned by Eugene, Euclid is so far the only space mission that requires or has as an essential part of the processing and of the design and of the project, the pairing with ground data such as DES, LSST, and as Eugene also said, PenSTARs quite likely. The launch is going to be in September 22, which isn't that far away anymore. So we need to step up and we need to be prepared for that, which I think we are. The science goals of Euclid, also again, this is my list here. Basically, Euclid should answer the next big questions of cosmology, expansion of the universe. We do a weak lensing analysis, and we do that by analyzing the galaxy clustering. As part of that, we will have millions and millions and millions of redshifts, of photometric redshifts. And at the end of the day, I mean, as also any modern mission, we hope that most of the science is going to come from the legacy science after Euclid has been closed down and after the data is all done and published. What is tiling? So you see here, in the yellow, you see here the survey area, about 16,000 square degrees. Basically what we need to do for our science, we need to photograph the entire usable sky. Usable sky in the sense that all the sky that isn't, polluted by lots and lots of stars because it's in the galactic plane, and that doesn't have a large background because it's in the Euclid, in the ecliptic plane. So in yellow, you see the large areas of the Euclid wide sky survey, wide field survey. And in green, you see the three fields of the deep survey. And so tiling is finding solutions on the questions how to best split up this kind of huge survey area for object detection and later also on object storage. It sounds trivial, but at the end of the day, it doesn't seem to be so trivial. So what are the requirements for the tiling? So on the right, you see a very, very coarse overview on the Euclid processing, data processing. So the object detection is taking place, plus the photometry, plus all the object characterization is taking place here in MIR. So we get the images from X, NIR, and VIS from the different cameras. And we do the object detection, and then we share that to our customers, to SIR, Photosat, Shear, and also to LE3, who do the cosmological analysis. So here we need to have a reasonable tiling in the sense that we need to be able to process it in a reasonable time. The input data needs to be also reasonably large. The fields or the tiles, they are not allowed to be too large because of projection effects. Of course, we need to cover the entire survey area. We need to be able to deal with extended objects of different size. And quite important, we need to guarantee a unique association between each object and a tile. That is because the units of the object detection will be the units of the further analysis of the cosmology and so on and so forth, in the sense of not the individual objects are going to be stored in the archive, but basically per tile. And so what we really need to avoid is to detect objects twice, because that would be a nightmare then for all kind of cross correlations and so on and so forth. The tiling needs to be adjustable because we need to adjust to survey plans, which are not really static. I mean, you know, the exact way on how what exactly is going to be covered is going to change over time. And we need to be able to support the processing planning. So at the end of the day, a tile is defined, you can see here on the right side, is defined by a central position and a size. Adjacent tiles, neighboring tiles, they do have an overlap. This is to avoid border problems. I'll come to that later on. But what is maybe new in Euclid is that each tile, we have an extended area, which you see here in blue, or in blue, yeah, blue shaded. The extended area is basically the image area where we do the object detection on. And we have a core area. The core area is the pink area here on the right side. While the extended areas, they do overlap, the core areas do not overlap and allow a unique detection of the objects. And for the core area, we define the core area in Hilpix indices, which does have some advantages in the sense that the Hilpix indices, they are defined on the sky, and you don't have any kind of projection effects. And here on the right, you see the Hilpix indices not by themselves, but with the multi-object, multi-order coverage in order to save space. The current base solution that we have for the tiling based on the current reference survey is that we orient the tiles in RADEX. So it's an astronomer or science-friendly orientation. We do, of course, simple square tiles with 32 arc minutes square. We do have a constant overlap with 2 arc minutes. The tiling starts simply at RADEC 00, and the tiles are placed in stripes at constant declination. And then we just step on in right ascension, and we adjust the steps according to the 1 over cosine declination, blah, blah, blah. We do a size adjustment at the border of the tiles in order not to space, in order not to waste the processing time and storage. And the Hilpix indices, we can choose the granulation to which we go. And right now, we think that NSide 13 is a very good choice to define the core area. Based on that tiling and based on the newest reference survey, we come to these kind of situations. You have here on the upper left, you have a normal tile scenario, very, very boring. You know, they are just square tiles and in pink, and the green shows the underlying Euclid pointings. But at the border, which you see in the upper right here, you know, here is the end of the survey. Up there are more observations of Euclid, and we adjust the tiles. So you have in that area, you have many, many small tiles. We adjust the tiles if the coverage of the survey, if the coverage of a tile is smaller than 60%, but that is adjustable, of course. And then you have also an interesting phenomenon at high declinations, like in the lower right here. We go to 87.5 degrees in declination, and you have all kind of projection effects, which are a bit exaggerated here because the plotting is in constant RADEC, but you have to adjust for that to get the good overlap. Well, the overlap is a quite interesting quantity. Without an overlap, as you can see on the figure on the left here, it just happens that galaxies are at the border, and you cannot measure the photometry and all the objects because they are at the border and they fall on different tiles. So to avoid that, you give them an overlap. And of course, the overlap size then is correlated to the maximum object size that you can resolve with your tiling. Note that here is a very, very big galaxies, but we come a very, very big galaxy, which is even in that scenario won't be covered correctly, but we come to that later. So roughly speaking, a 2 arc minute overlap gives you a 2 arc minute maximum object size, but that's a disadvantage of the Hilpix. The borders of Hilpix are jagged and they are not really, really aligned. So they are not really aligned with your tiling in RADEC. what we do to deal with that is we measure the minimal distance between the core area and the image border. And that we have done here for a large range in declination, basically for, from the lowest declination to the highest declination. We have adjusted at high and low decks. And in that tiling that I showed you in 2 slides before, we basically can guarantee that the minimal distance for each tile from the core area to the border is 30 arc seconds, which means that the tiling is sensitive to objects which are smaller than 1 arc minute. Good. But unfortunately, we do have larger objects. Right now, the Euclid reference survey, we break for nothing. So we don't break for large stars and we don't break for large galaxies. And so there are large range of Messier type galaxies inside there, which we have to take care of. And the plan to do that is to do special tiling for large objects. So instead of on the left that we do homogeneous tiling also for large objects, we do a special tiling and we make extra large tiles for every large galaxies, basically down to the 1 arc minute that we can guarantee a coverage. Of course, we have to go into archives to find out their positions and to plan for those tilings, for those tiles.
2 minutes.
Yes. Similarly, we do have several tiling strategies for the deep fields. Deep fields are 40 square degrees. And if you do the normal tiling, you will have an awful lot of input in the sense that even in the normal tiling, the input per tile is on the order of 70 or 100 gigabyte. The deep fields are 40 times larger. So you have to multiply this by 40. So you get to really, really large numbers of data that you need to assemble. And in order to deal with that or to be able to do that, we plan to do a special tiling for the deep fields and seamlessly put them into the normal tiles, into the wide field tilings inside there. Also, a good thing about the tiling is it is foreseeable in the sense that the input, which is the reference survey, we know exactly when each tile is going to be observed. As it is depicted in that frame, in the sense that, that the tiles at the top, they are going to be observed, the Euclid observations at the top are going to be observed at a certain day, and the observations at the lower with a dashed line, they are going to be available some days later. So what we can do is we can compute the intersections between the observations and the tiling. We can map the observations to the tiling, so we know that the filling status of each tile, and we can basically plan based on the tiling and the reference survey, the processing status. So we can anticipate when each tile can be run or can be processed under certain conditions. So one conditions that we favor is, okay, we process all tiles only if all the data is going to be available, which may take long for certain areas, because in certain areas, the neighboring observations are going to be half a year later or a year later. But also we can, of course, loosen these kind of prescriptions by saying, okay, we want them to be 80% full or something like that. That can be necessary in the sense that downstream analysis for shear and for the slitless spectroscopy may need our objects. And so we have to loosen up that. And basically at the end, and here I come to the conclusions, the tiling for Euclid needs to be planned for, because we have a large amount of data. The survey area is large and rather complex, because it contains basically everything. And also it's not only Euclid observations alone, but there are also several ground-based surveys are involved into that. The tiling is quite central, amazingly central. I didn't think about that, or I couldn't envision that when I started that, because it starts from the survey planning down to the data processing. Current solution, we envisage, we think to have about 64,000 tiles. It is adjustable. It takes us a couple of days, 2 or 3 days to compute a new tiling solution and to validate the new tiling solution. And what we still have to do, and what we are going to do now in the following months, but we still have time, is to do the special tilings for the deep fields and for the large objects. And I thank for your attention. I'm open to questions.
Thanks very much, Martin. Do we have any questions? Please put your hand up on Zoom or write a question in the Q&A box. From Andrea Modigliani. How do you combine the tiles together, resampling and mosaicing?
Now that's the point, we don't do that. So basically the mosaicing is per tile, and the resampling, everything is basically per tile, and then also the object detection and photometry is per tile. I mean, that's the central aspect of that. And then afterwards, when we have the object detection and the photometry and everything, we put the data, the object catalog for that entire tile onto the archive. And then the analysis, cosmological analysis, 2-point, 3-point, whatever point correlation function is run on based on those tiles.
Thank you.